Uh-huh. So when it comes to telling the difference between uh, dispersion forces and dipole-dipole forces, what we're going to be looking for is really just, does it have dipole-dipole? Because everything has dispersion. So we don't even really want to ask the question, does this have dispersion? The answer to that is always going to be yes. Everything has dispersion because everything has electrons. And so everything is going to have dispersions because of that. So really the question is, does something have dipole-dipole forces or not? And so what we're looking for there is we're trying to determine, number one, do we have polar bonds? And then number two, actually it might be easier just, let me pull something up real quick. Okay, can you see that? Can you see the slide again? Okay, so this first question here, does the molecule contain polar bonds? The way we determine that is, are there two atoms bonded together in the molecule where the differences between the electronegativities are greater than zero point 0.4? So somewhere, and I guess I don't have it here, but in the book, you can find a big table um, that just shows the periodic table, and it has all of the electronegativities listed. And so you're going to look at the different molecules. So for example, if we had this molecule. So we have carbon, and it's bonded to two chlorines, and it's also bonded to two hydrogens. So what we're going to do to try and determine if we have polar bonds is we're going to look at each of these bonds, look at the electronegativities of the things that are bonded together, and see how much they differ. So if you look at the electronegativities on that table, what you'll see is chlorine is 3. That's its electronegativity. Carbon is 2.5, and the hydrogen is 2.1. So those are the electronegativities, and like I said, you can find those on a table in the book. And so if we compare the electronegativities, carbon and hydrogen, the difference between those two is 0.4, because we have 2.5 and we have 2.1. So that's a difference of 0.4. Those bonds are not polar because they have to have a difference greater than 0.4 to be polar. So they're right on the line, but they are not polar. The carbon and chlorine bond, on the other hand, because we have 3 and 2.5, those have a difference of 0.5. And so that is a polar bond. And so we have two polar bonds here in this molecule because we have the carbon bonded to two different chlorines. So that answers our first question here. So the first question was, do we have polar bonds? And the answer is yes, we do. Now, we can't just then say, okay, the molecule is polar, therefore it has dipole-dipole. We can't do that yet. The next thing it says to do here is to draw the Lewis structure. Most of the time I actually just do that first because it's usually not too much trouble. But you need something that shows how everything is connected together, which then allows you to answer the next question, which is, does the central atom in the molecule have any lone pairs? Now this is assuming that it's a fairly simple molecule, and if it's a more complex molecule, then it's very difficult to get any kind of symmetry. So this is asking for relatively simple molecules like this one, where it's just one atom in the middle and then stuff attached to it. Do we have any lone pairs on that central atom? So if you remember, lone pairs are something like on water. So these pairs of electrons, those are what we call lone pairs. On this particular molecule here, the one we were just looking at, it doesn't have any lone pairs on the central atom. The chlorines have lone pairs, but we don't care about those. We only care about the lone pairs on the central atom. And so the answer to this question is no. We don't have any lone pairs on the central atom. So then the last question is everything attached to the central atom the same? And if the answer is no, like it is here in this case, then it's a polar molecule. And so this molecule can participate in dipole-dipole interactions. So if you have a polar molecule, it can do dipole-dipole. If you have a nonpolar molecule, then it would be it would only participate in dispersion forces. So if we had something like this, which I think was one of the examples that I talk about in one of the videos, if we have carbon tetrachloride, where every single...
Could you repeat the thing you said about polar? If it's polar, it has dipole-dipole, and if it's non-polar, it's what?
So if it's a polar molecule, it will have dipole-dipole and dispersion, because again, everything has dispersion. No matter what else is going on, you will always have dispersion. But if it's a polar molecule, it will have dipole-dipole. If it is nonpolar, so it does not have any, the molecule itself is not polar, then it will only have dispersions. So dispersion is the only option for molecules that are not polar. So this molecule here, even though every single bond in the molecule is a polar bond, because they're all polar and they're all pulling at the electrons in opposite directions, they cancel each other out. And that happens decently often, which is why we can't just stop with this first question. So the first question asking if we have polar bonds, very often if you have polar bonds, the molecule will also be polar, but it's not always the case. Sometimes you will have polar bonds, but the molecule itself is not polar, which is why we have to work through the flow chart here.
Okay. Then what's it called? Also had some questions, like 2 questions on the homework I was trying to complete. I didn't know like even how to start it.
Okay, which questions were they? Was it, I think I remember, was one of them about the gas and like how large would the container have to be for there to be no liquid? Was that one of them, or is that someone else?
Oh, yeah. That was me.
Okay. I'll go ahead and let's work on that one right here. So just ignore that question up there. It's a different question. Just this slide has enough space for me to work on. So the way that question is set up is it's going to require you to use the ideal gas law to solve it. And the really difficult part is figuring out that you need to use the ideal gas law and how that's related to it. So essentially what the question is saying is you have some kind of container and it has a lid on the top and there's a little bit of water in that container, just a small amount. And if you remember what I talked about in the videos, water is going to evaporate spontaneously. It'll go into the gas phase, and this happens at every temperature, not just at the boiling point, but it's always evaporating. But if it's in a closed container like this, if the container is too small, not all of the liquid will evaporate, because you'll get enough water up in the gas phase that some of it starts to get recaptured back into the liquid, and so you get what we call a dynamic equilibrium, where some of the water is evaporating, but then some of the water is going back into the liquid phase, and those are at equal rates. Both of them are happening at the same amount, and so you don't lose all of the liquid. But if the container is big enough, if you have a really big container, the liquid will all go into the gas phase you'll get it all to go into the vapor phase before you reach that equilibrium, and so essentially all the water will evaporate. And so the question is asking, how big does this container have to be to hold all of that gas without it turning back into a liquid? And so I think, if I remember correctly, in the question it gives you the mass of the water, and I think it tells you the temperature, and it tells you the vapor pressure of water in that at that temperature, because the vapor pressure of water changes from one temperature to the next. And so what you're going to have to do is give the information, or take the information that's given to you, and find the pressure, which is pretty much just given to you in the problem, because the pressure that you're given in the problem you can just plug in as P here in the equation. V is what you're trying to look for. That's your goal, is to figure out what volume do I have to have. You're given the mass, but you know how to convert mass to a number of moles. Just use the molar mass of water to do that. So you convert mass to moles, and then the moles you can just plug in. And like I said, I believe they give you the temperature as well. They pretty much have to give you the temperature, so you can plug the temperature in. And then R is the gas constant, which is just a 0.08206 liter atmospheres per mole K. And so you're given everything you need there, although you have to do a little bit of conversions with some of them to plug in and solve for V. So you would end up with that. So you would just divide both sides by P to get to the volume by itself. And so that should give you the correct answer if you plug all those things in. I don't remember what the answer should be, and actually I think on that question, I think every student gets a slightly different mass or a slightly different temperature or something like that, but it's the same question overall. Does that make sense?
I guess kinda.
Okay, if you go back and you try to work through it and it's still confusing you, like I said in my emails, I'm recording what I'm doing right now, and I'll upload this onto the YouTube site. So you can go back and you can pause me as I'm talking through this stuff, and hopefully that will be helpful in working that out.
Okay.
Alright. Did you have any other questions about other problems?
Yeah, I had one more question.
Okay.
Do you want me to go ahead and like read it off?
Can you hear me? What was the starting temperature?
It said negative 114.5.
Okay.
So it says how much heat energy is required to convert 81.1 grams of solid ethanol at negative 114.5 to a gaseous ethanol at 182.1 Celsius.
Okay. And so then it gives you the heats of fusion for each of those and the specific heats. Is that what it gives you after that? The heat of
Yeah, it gives you
vaporization?
it has the fusion of ethanol as 4.60 and the molar heat evaporation as 38.56.
Okay. And are those joules per mole? Does it give a unit with those? Okay. Yeah, kilojoules per mole. Okay. So, and does it give you the specific heat capacities for them as well?
Yeah, it says the specific heat capacity of liquid ethanol is 2.45 joules slash gram Celsius, and that of gaseous ethanol is 1.43 joules slash gram.
Okay. Um, does it give you a
Do you want me to
CS
go
for
ahead?
the? Does it give you a CS for the solid as well?
Mm-mm.
Okay.
Do you want me to go ahead and email it to you?
No, I think I have almost everything here. I think the only thing I'm missing is the melting point and the boiling point. Does it give those to you?
Oh, the melting point, it says it's negative 114.5.
Okay. So yeah, so that's why they didn't give us a CS for the solid. And then the boiling point, does it give us that as well?
Yeah, it has 78.4.
Okay. So this should be everything that we need to solve this. So essentially what we're doing here is we are taking ethanol that is right at the freezing point and we are heating it up to where it is well past its boiling point. And so in doing this, we're actually going to go through four different regions, I guess you could say. So we're starting here at the negative 114.5, and we're going to heat it up until we hit the melting, well, I guess we're already at the melting point. So we're going to heat it up until we completely melt it. So it's starting frozen, if I remember correctly. It's starting frozen. We have to heat it up to melt it. So when we do that, it's still at 114.5, negative 114.5 degrees, but now it is liquid. So it was a solid before. It takes a certain amount of energy to liquefy that sample. Then we're going to heat it up some more until we reach the boiling point, which is 78.4 degrees C. And at this point, it's still liquid. But at 78.4, we're going to add some more energy in to convert it into a gas. So then at that point, we'll be at 78.4 degrees C and add in more energy until we hit that final temperature, which was the 192.1 degrees C, which it'll still be in the gas phase at that point. So we have essentially four different regions where we're putting energy in. Two of these regions, we're putting energy in to change the phase. So that's these two regions here. So we have to put energy in to melt it, and then we have to put energy in to boil it. And then in the other two, we're putting in energy to raise the temperature. Does that make sense so far?
Yes.
See how we're melting it, heating it up, boiling it, heating it up some more. In each of these four regions, we're going to have an equation to figure out how much energy did it take to do this process. For the phase change regions, it is just going to be using these heats of fusion and heats of vaporization. So each of these tell us, so the heat of fusion, for example, tells us it takes 4.6 kilojoules to melt 1 mole of ethanol. And so what you'll do is you'll work out, well, I have 81.1 grams of ethanol,
Mhm.
and you'll use the molar mass to figure out how many moles that is. And actually, I don't know the molar mass of ethanol off the top of my head. But you'll use a certain number of grams for every 1 mole,
Mhm.
and that will give you a number of moles that you're working with. This number of moles then can be multiplied by each of these two heats of fusion and heat of vaporization. And when you do that, it will give you the number of kilojoules of energy it takes to melt it and vaporize it. So just take that number of moles, multiply it by this. That'll tell you how much energy this section needed, how much energy it took to melt. And then take that same number of moles, multiply it by the heat of vaporization, and that will tell you how much energy it took to boil it. So those are those two regions there. The other two regions are also very similar to each other. Those two regions, you have to use this equation from Gen Chem 1. Do you recognize that equation? So it's the heat.
Uh,
Heat is equal to mass times specific heat times the change in temperature.
yeah, I think so.
Yeah, so we have the Q here is what we're trying to look for, because the question is asking for how much energy does it take. And so we're trying to find Q, which is heat, which is just another way of saying an amount of energy. And that is equal to the mass, which we know, it was given to us, times the specific heat, which was also given to us. But we have to be careful to use the right one, because there's different ones for the liquid and gas. So that we know. And we also are given the information anyway to find the change in temperature. We're not just straight up given it. But we know, for example, for this section here, when we're heating it up, when we're increasing the temperature, we go from negative 114.5 up to 78.4. And so to find delta T, you are always doing final minus initial. So for that one, it would be 78.4 minus negative 114.5. And so you'll get a pretty big change in temperature there. Actually, let me just plug that in real quick. So that delta T would be 192.9 degrees C. So that would be the delta T for this region, and it would be a different one for this one. Here it would be 192.1 minus 78, so it would be a little bit less. It'd be something around 160 or so. Oh, sorry, not 160, 120 or something like that. 110, 120 would be the delta T for this region. So, and the mass will not change. The mass would be the same for this region and this region. The CS will be different, because here we have liquid, here we have a gas, so you would just plug in whichever one of these is appropriate. And then the delta T would be different for each one. But you can use the same equation for each of those regions. Solve for Q. You should end up with a number of joules, because the masses cancel and the degrees C cancel, just leaving you with joules. And so you'll have 4 different amounts of energy. So you'll have the energy it took to melt it, the energy it took to raise the temperature in this region, the energy it took to boil it, and the energy it took to raise the temperature in this final region. And so your final answer would just be all of those added together, because that would be the total amount of energy that it took.
All right. Thank you.
Mm-hmm. And this is definitely, if not the hardest, one of the hardest questions on this homework for sure. I've, yeah, I have had other students asking questions about this as well. So it's definitely a challenging one. But hopefully, with what you have here, you can work through it and figure this one out. If you go through this
Yep.
and it still is telling you have the wrong answer, feel free to email me again and I can try and help.
All right. Awesome. Thank you.
Uh huh. Anything else?
No, that was it. Thank you.
All right. You have a good night.